Hello class, this is Dr. E again. We're continuing our chapter on science, a way of knowing. And in the last video lecture, we talked about the importance of mathematics and units of measure. And we're going to continue to talk about units of measure. In particular, we're going to talk about time. And we'll talk about the importance of standardization of the units of measurement and the metric system. And then we'll talk about some related topics, precision and accuracy. Okay, so first let's move on to time. What is time? Well, time is the dimension that keeps everything from happening at once. Think about it. The most obvious measurements of time we have are the year and the day. The year, of course, being the length of time it takes for the Earth to go around the sun, one orbit around the sun, and the day, how long it takes for the Earth to rotate on its axis. So these units of time are determined by astronomy, essentially, and there's no debate about them. But we also have units of time, a month, and hours. Why do we have 12 months in a year? Why the number 12? Why not 10? Why not 5? Why not 20? Well, there are various thoughts about this. Perhaps the number 12 was used because of the signs of the zodiac. Or perhaps 12 months was chosen to make sense of the lunar cycle, which is about 28 days. So there could be about 12 of these lunar cycles in a year. Of course, we know that that's not exactly right because we can have months with 2 full moons. Or perhaps it was to align with the human female fertility cycle. There's some logic for each of these as being the basis for selecting 12 months in a year. But then the question is, what about hours? This next smaller unit of time. Why do we have 24 hours in a day? Again, why not 6 or 10 or 20 or 40 hours in a day? There's some thought that it's related to the Babylonians' use of a number system based on 60. Of course, you could say 24, 60, but there were some factors that would be in common with those two numbers. And then the next smallest measures of time, of course, are the minutes and the seconds. Why do we have 60 minutes in an hour and why 60 seconds in a minute? Some of these things, in retrospect, are somewhat arbitrary. The length of a year and a day are obviously set by astronomy. But the length of time of months and hours and minutes and seconds is somewhat arbitrary, but it was determined by human society, human culture. There is some thought that the numbers 12 and 24 for the hours in a day are based on the ancient Egyptians' use of sundials, in which they divided daylight period into 10 units. 10 units of daylight plus a unit of dawn and dusk. So that would be 12. And then they rationalized that if there were 12 of these divisions, when the sun was above the horizon, then there should be 12 divisions of darkness. So 12 plus 12, 24. And it turns out that most major ancient civilizations landed on the numbers 12 and 24 for the number of divisions in a month and in a day. Now let's talk about the importance of standardization in units of measurements. If you remember in our last lesson, we talked about a cubit from your elbow to the tip of your middle finger and how different people would naturally have different lengths for their elbow to the tip of their finger. And also there were different masses for stones. And in some societies, the stone may have been 16 pounds, what we now call pounds, and some it may have been less. And so it was important to standardize some of these units of measure, not only for science, but also for commerce and for building. It's interesting that in the Magna Carta, written in 1215, one of the first major governmental documents, King John wrote that there shall be a standard measure of wine and corn and ale throughout the kingdom. Okay, it's important. Later, in 1668, a number of countries got together in France to develop what is called the metric system. And the principal units of the metric system are the meter, the kilogram, and the second, plus some others I'll mention in a second. But the meter being the unit of length. A meter, as you probably know, is a little bit longer than a yardstick. I have with me my trusty yardstick, 36 inches. The meter stick then is a little bit longer, 3.37 inches longer. You're probably a little surprised that a chemist relies on a yardstick instead of a meter stick, and I guess I need to practice what I preach and try to find myself a meter stick to have around my house. So a meter is the standard unit for measuring length. A kilometer, which is 1,000 of these meters, is a little over half a mile, 0.6214 miles. So if you're running a 5K race, that's maybe around 3 miles. The standard unit for measuring mass is a kilogram. A kilogram is 2.2046 pounds. Now, what are some things that in your daily life weigh a kilogram? An average size melon is a kilogram. A medium to large size textbook would weigh about a kilogram. A bottle of wine would weigh about a kilogram. Your standard 500 milliliter soda bottle weighs about half a kilogram, just to give you some idea. Related to the kilogram is a gram. So a kilogram is 1,000 grams. And also on this slide is shown the relationship between grams and a pound. And the standard unit of time is a second, which has been with us for a long, long time. Of course, how long is a second? How long it takes to say 1 Mississippi, 2 Mississippi? Yeah. Just think it could have been 1 Nile, 2 Nile. All right. Other units of measure that we have are the Kelvin for temperature, candela for light intensity, ampere for electrical current, and the mole for the amount of substances. The metric system is preferred by scientists and engineers, and the reason is because it's easy to use. It's based on the decimal system. So for whatever unit you're talking about, such as a gram, if you had 10, you would have a decagram. If you would have 1,000, you would have a kilogram. If you'd have 10 to the 6, you'd have a megagram. We don't use that term very often. But we have these multipliers, kilo, mega for 10 to the 6, giga for 10 to the 9th, and tera for 10 to the 12th. Tera would be a trillion, giga would be a billion, mega a million, kilo 1,000, for example. And then if you go smaller, for example, if the base unit is a meter, then we have a centimeter, 0.01 meters. We have a millimeter, even smaller, micrometer, nanometers, picometers. So these multipliers allow us to use one unit of measure and then scale it up or scale it down by adding these prefixes. Just to give you some idea about a centimeter, which is something we use quite often, the width of your fingernail on your pinky is about a centimeter. Also, a gram. How big is a gram? We said a kilogram is about the size of a melon, but 1 gram is about the size of a M&M. A peanut M&M weighs about a gram. It's a little bit bigger than a gram, maybe 1.2, 1.3 grams. But give you an idea of the size of some of these metric units. I want to digress for just a minute and talk about the meter, which I think is fascinating. The meter was first defined in 1668 as the length of a pendulum that makes 1/2 a cycle in exactly 1 second. I think this is interesting because it shows a connection between distance and time. Now, what do we mean by that? As I said, I don't have a meter stick, but I have a yardstick. So what this means that if we start the yardstick or the meter stick, it should be, swinging, for each half cycle, that is going up half a cycle, each half cycle should take 1 second to traverse if the arm of the pendulum is 1 meter. So relationship between time and distance. Actually, the seconds pendulum is now known to be a little bit off from a meter, but look how close. 0.994 meters would be the length of the arm to have a half period that lasts 1 second. So the initial definition of a meter was based on the length of a pendulum arm, along with our definition of time in seconds. Later, the meter was defined as 1/10,000,000th of the distance from the Earth's equator to the North Pole. So if you look at the drawing in the bottom right, from the equator to the North Pole would have been 10 million meters. 10 million meters would be 10,000 kilometers or kilometers. And that was the definition of a meter that was established in 1791. Now, how close is that? Actually, it's pretty close. If you extrapolate it and go around 4 quadrants to make a complete circumference, you would predict then from this that the circumference of the Earth would be 40,000 kilometers. Actually, the circumference of the Earth is very close to that. It's only about 75 kilometers off of that 40,000 estimate from the definition of a meter back in 1791. Now, since that time, we've defined the meter in other ways, including the length of standard meter bars, which are made of particular metals, platinum or iridium, at a particular temperature. And also, the most recent definition of the meter is in terms of the speed of light. The distance that light travels in 1/, this number that looks extremely complicated, but this is actually the speed of light. So a meter would be the distance traveled by light in a vacuum in 1/, the speed of light, the numerical value of the speed of light. So a little bit about the history of our definition of a meter. Now, concepts of precision, accuracy, and errors. And we want to cover this because it's very, very important to scientists and engineers to have experimental data be reliable. The terms precision and accuracy may seem to you like that's the same thing, but it's actually not. Two different things. Precision is how well repeated measurements agree with one another, and accuracy is how close the measurement is to a true value, if in fact the true value is known. The precision and accuracy of measurements can be compromised by errors. Errors which can be either random errors, such as that due to electrical noise, just random, or systematic errors, which might be due to a miscalibration of an instrument. If you look at the bottom right-hand slide, this shows you graphically the difference between accuracy and precision. Let's start by looking at the bullseye, which is labeled 3. If we imagine this as being a bullseye in which we're shooting arrows at the bullseye as our experimental measurements, you see that in number 3 you have a very tight pattern. All of your measurements or all of your arrow shots would pack very close together. Very precise, very well repeated, but not necessarily near the true value. Conversely, if you look at pattern number 2, a lot of scatter in the pattern, but on average, that average would be at the bullseye. So that would be an accurate measurement. Obviously, what we would like is to be able to make measurements that are both accurate and precise. And that's what is represented in number 4, where we see both a tight pattern and it's right at the bullseye. Now, random errors can often be handled by repeated measurements and use of statistical methods. Systematic errors can be more problematic, especially if we do not know that the systematic error exists. Okay, we're going to pause again and have a little quiz, and the next time we will talk about the scientific method and some of the characteristics of the way science is done. See you shortly.